Hello and welcome to my video presentation. My name is Michael Heisel. Today I'll be talking about the momentum flux budget, and I'll specifically be exploring a structural model to represent the turbulent transport of momentum flux in the roughness sublayer. My colleagues for this work are Marcello Ciamecchi from UCLA, Gabby Cattoul from Duke University, who is a real driving force for this work, and Michele Guala from St. Anthony Falls Laboratory at University of Minnesota. I want to start by looking at the first order closure of the momentum flux, which is traditionally by K-theory or gradient diffusion. You can see that the momentum flux is related to the mean shear using some sort of diffusivity constant represented here by K1. There's a direct link between K-theory and important applications. For instance, in large eddy simulations, the equilibrium wall model is often used to estimate the shear stress at the lowest grid point. This wall model is based on the law of the wall relation, which is closely linked to the K-theory expression shown at the top. We know K-theory works well within the inertial layer, where there is a logarithmic form for the mean velocity and there are inertial dynamics for the velocity statistics. However, if we're hoping to model the momentum flux in the roughness sublayer, there's more uncertainty about how well the gradient diffusion closure works, and that's really the impetus for the study today. Here, I'm extending the momentum flux to a higher order closure. This can be done by first returning to the full momentum flux budget and then using the assumptions listed at the bottom of the screen. The contributions that we now have are from production by the mean shear, which is simply the K-theory term from the previous slide, and we are no longer neglecting the transport by turbulence. We have experimental measurements in roughness layers that I'll be introducing later on, showing that transport can contribute more than a quarter of the overall momentum flux near rough surfaces, which is really motivating the need to include representations of transport when we're looking at rough wall flows. This provides us with the goal of coming up with a model for this higher order term, UWW, which will help us to more accurately represent transport near rough surfaces. To explore this problem, we used experimental data from a number of different sources. The first source was direct numerical simulation, which is computational, and then the remaining sources are from wind tunnel measurements. The measurements of most interest to us are above the rough surfaces. For this, we have cylinder roughness from the Edinburgh wind tunnel. These results were digitized from work by Mike Raupak in 1980. Then we have woven wire mesh roughness, which is shown in the bottom left image. And these are our own measurements from the St. Anthony Falls Lab wind tunnel. And then finally, we have measurements of sandpaper roughness from the University of Melbourne. And these data were graciously shared with us by collaborators at Melbourne. Here I'm showing mean velocity profiles in terms of deficit from the freeze stream condition. The primary purpose for showing these profiles is to introduce the color coding that I'll be using throughout the rest of the presentation. Specifically, the orange coloring corresponds to the roughness layer closest to the wall, blue corresponds to the inertial layer or logarithmic region, and then farthest from the wall in the outer region we have the wake of the wind tunnel measurements. This region is the least analogous to atmospheric conditions, such that moving forward we're primarily going to be focusing on these two regions nearer to the wall. The basis for the structural model that we'll be deriving is sweeps and ejections, and specifically the balance between contributions from sweeps and ejections to the overall momentum flux. If you're familiar with much of Gabby's work, you know that he likes to use this statistic. And specifically, what we're looking at is if we quantify the sweep and ejection type events that exist within the flow, and then calculate the sweep and ejection contributions to the overall momentum flux. This delta SO parameter represents the difference in the fractional contribution of sweeps and ejections. Here I'm showing profiles of the delta S statistic for all of the data sets, where negative values of delta S indicate that ejections contribute more to the momentum flux than sweeps, and likewise positive values indicate that sweeps are favored. What you can see is that throughout the inertial layer, the delta S value is fairly constant around -0.1, indicating there's a slight preference for ejections. However, as you move deeper into the roughness sublayer, there's a tendency for sweeps to become more and more favored. Now this profile looks nice, however it doesn't really help us towards our goal of the structural model, where it doesn't provide us with any information about how delta S is related to UWW. To make this connection, we can turn to cumulant expansion methods, or CEM. In CEM, you estimate a probability distribution, or PDF, by choosing a base distribution. In this case, I'll be using a Gaussian normal, and then adjusting that distribution using higher order cumulants or moments. Here, I'm showing an estimated distribution of velocities based on some of our experimental measurements, and then the black line is the best fit of a normal Gaussian. We can improve this fit by tweaking the distribution based on this moment M30, where M30 is specifically accounting for the skewness. This MIJ notation is a standardized mixed moment of U and W, where M30 corresponds to U cubed over sigma U cubed. Cumulant expansion can also be used in joint distributions. Specifically here, I'm showing a joint distribution of U and W with the quadrants corresponding to ejections and sweeps indicated. I can adjust this joint normal distribution by adding information about the correlation of the two variables, how well aligned and correlated they are with each other, which is represented by M11. Then from the previous slide, we saw that M30 is a skewness parameter telling us how asymmetric the distribution is along U. Similarly, M03 is the asymmetry or skewness along W. And then we now additionally have these mixed third order moments. M21 is UUW, which is related to the transport of the streamwise variance. This kind of creates a triangular looking distortion to the distribution. And similarly, rotated 90 degrees, you can see the effect of M12, which is UWW, the transport of the momentum flux term. And in reality, all of these moments and their shapes do not happen in isolation from one another. When you combine all of their effects, you get a more realistic representation of the joint distribution for U and W. Back in the late 70s and early 80s, some very smart folks figured out how to relate this delta S parameter with all of these MIJ moments that I introduced in the previous couple of slides, and they came up with the equation shown at the top here. How well does this equation work? It turns out that it works very well based on our experimental measurements anyway, where the horizontal axis are the measurements of delta S, and then the vertical axis is the prediction from cumulant expansion representing the right side of the equation. And this has close alignment between prediction and measurements throughout the inertial and roughness layer. However, in order to use this expression, we see that the two parameters we're most interested in, delta S and M12, representing UWW, are fairly well mixed with a lot of other parameters that we're less interested in. So to make this more palatable, we need to work to reduce this expression and simplify it down. We can start to simplify our model expression by turning to insights provided by Mike Raupak in his 1981 study, where he demonstrated there's linear relations between all the third order mixed moments, and specifically he proposed the following functional relationships between these moments. And that was only for his cylinder roughness. What I'm plotting here are the same comparisons across a wider range of roughnesses. The dashed lines are the linear relations predicted by Raupak, and you can see that even though we're adding woven wire mesh and sandpaper roughness, there is still a strong linear relation within the roughness sublayer that's invariant with the roughness geometry. And this is going to help us to simplify our model expression, where now we can take all of these third order moments that are in the parentheses here on the right and then come up with this updated model equation. We still have this M11 term here that's preventing some further simplification, and that's what we want to investigate in the next slide. Here I'm showing profiles of the correlation coefficient M11. You can see there's some variability across the different experiments. However, the value is fairly close to minus 0.35 throughout the roughness and inertial layers. I specifically want to use this value to plug it into the instance of M11 on the right here, while leaving this instance in the denominator alone. I am only updating the value on the right because I want to be able to combine these two terms for the model simplification, and this is justified because the contribution from this left side is about 1/6 of the contribution from the right based on the value of M11. So using this simplification, we get the final model expression shown here on the bottom left, where we can make this dimensional to reach the expression given on the bottom right, where we see the transport of momentum flux is related to the momentum flux, the vertical RMS, as well as this balance between sweeps and ejections. Now that we have our final model expression, it will be nice to know how well it aligns with direct measurements. And for this, I'm comparing our results with gradient diffusion closure, where the gradient diffusion includes the gradient of the momentum flux, the TKE, and some sort of prescribed mixing length, and then the direct measurements of UWW are on the vertical axis. To achieve a similar range of values, I'm normalizing both axes by U star cubed, where U star is the shear velocity. You can see that we have some positive trends using gradient diffusion model. However, the prediction isn't very well aligned with the measurements. If we turn instead to the structural model that we came up with, you can see that there's close alignment between the model and the measurements, both in the inertial layer and then throughout the roughness sublayer, which is really indicating the strength of this structural model based on sweeps and ejections to predict the transport of momentum flux in the roughness layer. However, there still is the challenge of actually implementing such a model, where it would be helpful to have a priori knowledge of the shape of delta SO based on the parameterization of the rough surface. Here I'm replotting the delta S parameter, except now I am expressing the height in terms of the depth of the roughness sublayer, and you can see that delta S is closely intertwined with the behavior of the roughness sublayer, where you have invariant delta S in the inertial layer and then an increasing gradient in delta S as you go deeper within the roughness, which is indicative of increasing momentum flux transport. And based on the grouping of these values, there might be the possibility of parameterizing this profile based on roughness. However, at this time it will be left to a future study. Now, there are many works by Davide Poggi that have showed that the extent of the roughness sublayer is closely resembled by the behavior in this fractional stress contribution delta S, and we are finding similar results in our own work. To quickly summarize, we looked at the momentum flux budget and extended it to include the transport of the momentum flux by turbulence, and then closed that contribution using a model based on the imbalance between sweeps and ejections. The nice thing about this model, and one of the more important general outcomes of the study, is that the tuned parameters that contribute to this constant value appear to be invariant for the geometries tested. This indicates some sort of structural similarity of eddies within the roughness layer, where these eddies that are influenced by the roughness geometry are all leading to a similar change in these various statistics, such that the relations between the stress transport, the sweep ejection balance, and the third order moments are all maintained within the roughness layer. With that, I'd like to thank you for watching the presentation and point out that everything I talked about today is published in a new Physical Review Fluids article, and that the work was supported by the National Science Foundation and Institute on the Environment.